Okay, okay, static. Somebody give me your definition of static.
Not moving. Linear.
What?
Linear.
Linear. I heard not moving. Stagnant. You might could even say it might be something that, like for example, yesterday when we looked at those graphs, the car was moving, but if it was moving at a constant speed, that could still be static, even though it's moving. It's the speed is not changing, so that could be something that you see. What about dynamic? Fluid. Changing. Those are good. Changing. Variable. Right. So those are all possibilities. All right. So you've got 4 things here. For sake of time, I'm going to just write this out. So for the first one, it's constant velocity versus an accelerating object. So constant, we looked at yesterday, that'd be straight line, right? Accelerating would look like this. Yeah. So that's your first one. You're right. If it were right, if it was, it depends, and that would be with time and distance as your. Because that does matter a lot, because if you're graphing, for example, speed, it would look totally different. If you did time and speed, it'd look like this, but then you have this right here. Yes, this one, the first one is your pre-calculus, this is your calculus. Yeah. For the second one, it says slope of a line versus slope of a curve. So, slope of a line, that's very simple, rise over run, right? Then that form. But, slope of a curve, you can't really do that. So what we're going to figure out that we do is going to be, we're going to look at tangent lines at the point. So like if I want to know the slope of the line at this point, I'd use a tangent line. But if I want to know it at this point, it'd have a different slope, right? So that slope is changing.
So where besides becoming a speed radar would you use it?
This look like if you are like testing a lot of different things. First of all, let me tell you this about calculus because I haven't said this before. If you use calculus in your job one day, and you are not a math teacher, you are probably making a lot of money somewhere. Because this is high-level stuff that this is a high-level stuff that if you are actually doing calculus every day, you're at a pretty high level. Most people do not use calculus. So why are you here if most people do not use calculus? Several reasons. Number one, it looks good on transcript. Number two, lots and lots and lots of degrees, particularly if you're wanting to do anything with math or science, are going to require at least Calc 1, because they want you to have, like, a lot of it is physics, is based upon calculus, so they want you to have a background knowledge so that you can sort of understand where some of these things come from. And then, of course, there's a possibility that you might decide to do something that actually does need calculus, where you're like programming, doing like programming sort of stuff, data analysis, engineering, like high-level engineering, not low-level engineering, like high-level engineering, some of those things that you're going to use those for. And sometimes I just like to use it as a weed-out class. Like if you're going to be a doctor, you're going to have to take Calc 1, because a lot of times they use it as a weed-out class, which I'm kind of okay with. I want my doctor to be smart enough to pass Calc 1. I'm not saying they necessarily need to be like the greatest at it, but they need to at least make a C in Calc 1. Yeah. So you can do it. So a lot of this stuff would be like physics sort of stuff you'd be looking at. So like if you were designing cars, if you were like testing stuff that you guys test the speed of, like ballistic sort of stuff. We'll also see like if you're doing ballistic sort of stuff for the military, there's a lot of factors we ignore that you would have to consider that make it even more complicated than what we can do with calculating. So there's crazy stuff that can be done with this sort of stuff. I can't get into great detail because I am a high school math teacher and not a ballistics expert with the Army, so I can just give you an idea of what you might could do with some of this. Did I have you guys, if you have me first semester, did you guys do the Zoom meeting with my friend from Raleigh? Yeah. But if I had you second semester, we didn't do that, did we? I might need to bring him back. He's got some.
He had a calculus speech. I remember.
Yeah, he might be the only person I know that actually might use some calculus on a day-to-day. He works for SAS, which is a programming company in Raleigh, and they do a lot of data analysis stuff for, like, for example, whenever you have, like, your test scores, SAS handles all of that for the state of North Carolina, so whenever you take EOC, they get your data. They have all these formulas where they can, like, predict that Addison will make a level 4 on the Math 3. Sometimes they're crazy formulas, and I think they're idiots for coming up with it, because sometimes the kids' scores look like this. Here's 6th grade, 7th grade, 8th grade, and here's what they predict for them to do in 9th grade. But what would have been more accurate was, here's what's going to happen in 9th grade. So anyway, but he also, I know that his company's also doing, like, he has been doing a lot of stuff in Georgia because they were handling all of the, like, coronavirus analysis in Georgia. So, like, all the state data on coronavirus, they were doing that. He is actually a salesman. So what he did some of the programming at one time, but what he does is he, like, sort of translates between the nerds that do the programming and then the people who are needing their services, right? So, like, the business owners that need to analyze this data talk to him. He goes and talks to the nerds and tells them what they need, and because the nerds, they don't interact with people. They like to sit behind their computer, and yeah, so yeah, I'm a nerd, but I'm not this kind of nerd. Like some of the people that work at SAS doing their, like, more intensive programming stuff, like, are crazy. They're like crazy mathematicians. They're like, make movies about them. Like, I picture them with, like, stuff scribbled all over their walls, sort of mathematicians. I love math and I'm a math nerd, but I'm not that level of math nerd. So, I don't know that I have the intellectual capability of being that level of math nerd. Might be the reason. Yeah. But sometimes those people have a hard time explaining that to anyone else. So, yeah, that's where Albert comes in, because he is very smart, although he will tell you that he's not nearly as, whenever it comes to, like, programming, he's not nearly as smart as the people that are doing the highest level stuff. But he understands he understands the idea, so they can talk to him, and then he can talk to somebody who understands nothing about it, and it's just like working for the governor of Georgia, and then they can work together there. So it's a pretty cool job. I'll have to maybe we can do another Zoom with him, possibly. Okay, we're off topic. We need to get back. Alright, curvature of a circle is constant and can be analyzed with pre-calculus. Curvature of a curve is variable. So, like, for example here, if you have a circle, that radius is the same all the time. But if you have a curve, right, like our curve at this point, like right here, we might have this radius, but over here, right here, we might have, you know, a different radius, although those look about the same there. So I didn't pick the best points. I should have made it. Let me change that a little bit. There we go. So like your curve here, you've got that radius, whereas here you have a much bigger radius. Okay. And then area of a rectangle, this is very simple, right? You've been doing area of a rectangle since you were tiny. So area of a rectangle, length times width, super easy. But if you're doing area underneath a curve, that would be like this area. And you do not know how to find that. But I do. And I will teach you by the end of this this curvature piece. We will not do the curvature. We will do the curvature as far as like the radius of that circle. We will not do, but we will do all the other three in this class. All right. What tip does the author give you to try to learn calculus? Don't memorize formulas. It's not just memorizing formulas. So this is going to be an adjustment for you. That may, so, yeah. So if you are someone who, in order to do the homework, you go back and look at your notes and say this is step 1, step 2, step 3, step 4. And then you do step 1, step 2, step 3, step 4 over here, and it works out, and you got it. There will be some times that we do that in here. But there's also going to be a lot of, like, understanding the bigger picture that must go on, which is going to be excellent for your brains and make you so much smarter. But it is also a little bit painful sometimes because it is more difficult to do. That's right. Right. Because it is like, think of your brain sort of like a muscle, right? If you go down there to the weight room and put a 45 on either side and push that weight up off of your chest, it's going to make you stronger, right? But it hurts. But it's the same in math. You got to do, now, if you go down to the weight room, you probably don't want to put like 4 45s on each side and try to lift that up off your chest. You might kill yourself. We got to work up too. All right, looking through 59 and 60, which without calculus examples were you unfamiliar with? Curvature of a circle we pretty much already talked about, right? We're not familiar with. Yeah, tangent of a sphere is one I do not expect you to know. And actually that is like 3D stuff, which is Calc 3, so we won't actually even get there. Yes, and you must know this if you want to be an engineer. You must have Calc 1, 2, and 3. So, and differential equations. Because my husband wanted to be an engineer, but he also was not always the hardest working in high school. So he had signed up for an extremely challenging class called problem solving his senior year for math. And so he went to NC State to visit, and they told him he was going to have Calc 1, 2, and 3 and differential equations to be an engineer. And he went into a little bit of a panic. And so they let him take calculus at Surrey second semester because he couldn't get into AP because it was already started. So if you are going to be an engineer, you will have to have Calc 1, 2, and 3 and differential equations. Some sciences require that as well. Like biology is probably not going to require Calc 1, 2, and 3. Most times if you're going to do pre-med, you're doing biology, they will require Calc 1, usually, which means you could get that done here. Or at least get familiar with it, so maybe it won't be so hard if you have to take it over. And then there's some other things. Of course, you'll major in math. You're going to need all those. Okay. Any other ones? Secant line. A secant line would be, so like a secant line, if you have a curve right here. A secant line is just a line that goes between 2 points on the graph. So, like our warm-up that we did, we were using secant lines there, so it goes between 2 points. Whereas that's pre-calculus because we can just find those 2 points and find the slope of that line. Calculus is when you do a tangent line where it's just at that 1 point.
So, the secant line is pre-calculus?
We did not, we probably didn't do secant lines, but it can easily be done just using pre-calculus like slope, right? And whenever the book uses the word pre-calculus, it doesn't necessarily mean the course pre-calculus. It means anything before calculus. So it might be in math too. But so you are already doing like slope of a secant line whenever you were like on the warm-up, whenever we were finding the slope of this line right here, that was your slope of the secant line. So
yeah, I just used the steps. So.
Yeah. All right. That's not right. That's pre-cal. That's not us. Okay. All right. Any questions about that stuff? Okay. So I just kind of want to introduce you to that. The main difference, stuff before calculus, we have to have things that are set, constant. Once we learn calculus, we can analyze situations where we have a changing speed or a changing acceleration, or we can look at a changing curve there. So that's our biggest difference. All right, get out those notes we were working on yesterday. We're going to finish those up. Yes, I've got one right here. Those didn't make it over there. That. All right. Let's see. Oh, wait. That's not all right, so we just got a few more examples I want us to look at here. All right, so I think this, let's see, we finished this part, didn't we? Average speed, yeah, we finished that. Okay, so this one, I'm trying to think of what that YouTube video right there was. And whether I want to watch it or not. Let's see how long it is. Is this the, oh, it is cool. Alright, we'll do this, we are going to watch it, it is cool. Yeah, they are cool. Alright, so, average rate of change. Okay? Your average rate of change is just your distance, well, it is your change over time, or in the specific examples we've been looking at, it was our distance traveled. So the change in the distance. Whereas, so this is over a span of time, right? Instantaneous rate of change is the rate of change, or in the examples we have looked at, it's speed, but it, as we'll see in the future, it can be something else. At a given moment in time. Okay, so we are going to watch this video. I think this is a really cool example of a place that calculus applies dealing with roller coasters. So, let's see.
How long is it?
It's 10 minutes, so.
G-forces are one of the things that make roller coasters so exciting. Rapidly changing and extreme forces in relation to everyday life for most people cause the body to feel in danger, which triggers the release of chemicals in the body, most notably adrenaline. The thrill comes from surviving the roller coaster. Of course, it is this controlled feel that provides the rush. G-force is nothing more than another unit of acceleration. It is designed as a more intuitive means of communicating the strength of different accelerations. The normal acceleration due to gravity on the Earth's surface is 9.8 meters per second squared, which is equal to 1 g. If you were to stand on the moon, a smaller body with less mass, where the acceleration due to gravity is 1/6 of that on Earth, you'd experience 1/6 of a g, or roughly 0.16 g. Whereas if you were to stand on Jupiter, a far larger planet than Earth, with greater mass, the acceleration due to gravity is around 26 meters per second squared, which also equates to 2.65 g. The same is true for accelerations we experience undertaking different activities in our lives. If you accelerate in any direction, it can be said that you're experiencing some additional g-force, as compared to just simply standing still. It is worth noting that acceleration must be thought of as a vector. That is to say, it has direction, just like velocity.
I didn't realize how much
It's like having a movie in a train taking a circular corner at a constant speed has changing velocity vectors, and therefore it has acceleration forces. In this example, the acceleration forces in both directions are resolved into one acceleration force towards the center of the corner. For you to remain in the seat and not be thrown from the train, the seat must exert a force on your body. It is this acceleration that is referred to as the g-force. For roller coasters, it is accelerations in all different directions that create the g-forces we know and love. Three commonly used types of g-forces on roller coasters are vertical g's, lateral g's, and acceleration g's. Vertical g's are the forces pushing you down into the seat, or up out of the seat in the case of airtime. If one imagines sitting in a roller coaster seat, vertical g's are the forces you experience at the bottom of a drop as the train pulls out and you feel heavy. In the same turn, airtime is the experience at the top of a hill that causes riders to feel weightless due to negative vertical g's. Lateral g's are the forces you experience sideways. A great example of this type of g-force is that found on wild house coasters, as the tight, unbanked corners provide lots of lateral g's, making the train feel as if it's tilting. Acceleration g's are the forces pushing you backwards into the seat, most often found during launches. Brake runs also cause acceleration g's. However, as they are negative, the train is slowing down. You are pushed forward out of your seat and into your restraints. In addition to these three main types of forces, there are also g-forces accelerated with the rotational aspects of track shaping. These forces, however, are often much harder to directly feel. most evident and most commonly felt type of G-force like this is the track rolling. The famous whip and B&M flat spins, or zero-G rules, are a result of this kind of rolling acceleration. The amount of G-force the human body can withstand is dependent on many factors. These can include fitness, training, hydration, and nourishment. Ever notice how you might feel lightheaded or black out on a roller coaster when hungry or thirsty on a hot day? The risks from experiencing high G-forces vary, but the key issues are a lack of or excessive blood flow to the head or disruption to internal organs. Frequently,
Okay.
is the duration of time that the G-force is experienced for. During a car accident, the human body may experience many tens of G-force. However, this is only for an extremely short period of time. Typically, however, we only refer to G-force that occurs over a period of time that can be measured or sensed. The average person can withstand G-forces of up to 6 or 7 positive G-force and negative 3 to 4 G-force for short periods of time without suffering too much long-term discomfort. That said, roller coasters are generally designed between the negative 2 to positive 4 G-force region to ensure rider comfort. The additional G-force you experience at the bottom of a drop that makes you feel heavy is a result of the train being accelerated away from the ground. The seats are exerting a force on the riders to change their direction. G-forces of less than 1 are a little more complex. Equations of motion give us some interesting results. An object launched into the air at an angle.
This is the quadratic, right?
We'll get air results, as is often the case in these kinds of thought experiments. The path the object will take is dictated by the acceleration due to gravity. During its journey along this path, the object is accelerating at the rate of acceleration due to gravity. Remember,
This is like your
that's
pumpkin.
9.8 meters per second squared
Pumpkin.
on Earth. In this instance, the object has nothing pushing back on it, meaning it experiences zero G. Roller coaster designers use this physics to their advantage. If the engineers calculated the path the train would take if the track simply ended, and then built the track along this path, they would have created a hill with perfect floater airtime. If the train was traveling faster than this track shape was designed for, the train will be forced to follow a tighter curve. At this point, the riders in the train, if not properly restrained, would leave their seats and continue on the previous path. As your bum leaves the seat, the restraints hold you back in place and leave your internal organs to experience the feeling of being accelerated upwards. By varying the sharpness of the curve, manufacturers can control the amount of negative G-force well. This form of ejector airtime is often popular with enthusiasts. Floater airtime is best experienced on B&M hypercoasters, which are famous for creating near-perfect zero-G force hills. It does, however, also explain the dreaded trip breaks. If the train travels over the hill faster than the design is allowed for, the train will be forced to stay on that path. By using a trip brake, B&M are able to ensure the train is traveling at just the right speed as it enters the element to get floater airtime. The final thing to consider is how engineers attempt to manage the forces you experience on coasters. This is not to say they try to make them less exciting, only more comfortable. Rapid changes in acceleration are unpleasant and can cause damage even if maximum G-force reached is not itself that high. This leads to two major aspects of roller coaster design: lead-ins and outs, and hardline. The concept of lead-ins and outs is a method of using some reasonably complex mathematics to gradually change the severity of the curve. Rather than simply having a section of straight track into a section of constant radius curve, it is much more pleasant to gradually blend the two. Anyone who has ridden an older roller coaster that doesn't exactly use this approach can know what I'm talking about. Hardlining is a little more subtle. If the track were to rotate around its center, then riders would feel as if they were being flung from their seats. If the track were to rotate around some position above the track, it would give riders the sensation of being tipped out of their seats. The latter of these is much more comfortable and enjoyable during high-speed elements. Roller coaster designers work using a notional point above the track called the heart line, so named due to its proximity to the chest level of riders. The idea of the heart line is to turn riders around their center of mass. The heart line varies between manufacturers and riding positions. For example, a sit-down roller coaster will have a heart line relatively close to the track, whereas a stand-up roller coaster would have a heart line relatively far away from the track. Equally, an inverted coaster would have a heart line underneath the track. Heart lining is responsible for some of the most complex and interesting track work found on roller coasters, and is especially impressive on inverted roller coasters. Whether positive or negative, large or small, G-forces are one of the fundamental parts.
I don't think I noticed that thing. Oh my gosh.
They're a complex subject with many resulting impacts on design, but they are without a doubt one of our favorite parts of coasters, especially extreme negative G-forces, something I think we all agree is the most fun.
Alright, so, yeah, that sounds like a road that my son would want to go to. Mom, what's the fastest roller coaster in the world? Mom, what are the top 10 scariest roller coasters in the world? Mom. Yeah. So, let's see where we're at. Alright, so, I just thought that was really interesting. Obviously, if anybody ever knows anybody who designs roller coasters for a living, I know that the most recent one they put in at Carowinds, the Copperhead, I think, road one, which is, it's not the fastest one, but it's crazy because you don't have shoulder straps, and they start off with one of those really slow rolls upside down, and you have no shoulder straps. Yeah, Fury doesn't have shoulder straps, but it doesn't go upside down. It is super scary. Even though it's got like that, what they were talking about, that weightless.
The Fury was terrible. Like, roller coasters are fun, but the Fury was just scary.
It's scary.
No
those straight down drops. Oh my gracious.
I felt I might get off this.
I'll do it, but then I'll regret that I did. So, I think I like the Intimidator the best. It's a little calmer, and you got a lot of that up and down. But, anyway, tell your neighbor your favorite roller coaster real quick and get it out of your system. Anybody who does not ride them, period.
My sister's husband, he rides motorcycles, but he doesn't like them.
Really? Motorcycles are much riskier. Yeah. Okay. So, let's get back to this. So, that was sort of an introduction to G-forces and sort of just a really cool video. I wanted you guys to see it because it had a lot of stuff we can kind of apply here. But that idea of a G-force, like right now, you are experiencing 1G pulling you down to the earth. You're always experiencing 1G vertically pulling you down towards the earth. You don't really recognize it. When we typically think of G-forces, we think of G-forces like on a roller coaster where it's in a direction other than down, right? To the left, right. It might be up or down, but it's in addition to what you are already feeling due to gravity. So, let's look at this. So the Porsche 918, which I just looked up. I don't know that much about these things because I prefer the minivan. But if we had one of these, it could go 0 to 97 kilometers per hour in 2.5 seconds. I don't remember why it was 97, but that's whatever it was where I looked it up. I guess that's 60. I guess I might have converted it from 60, I guess. Yeah. It's like your 0 to 60 time right here. Oh, that's too small. Let's go somewhere which way. Alright, so this graph gives the speed in kilometers per hour of the car after T seconds. So you'll not, like, if you have ever taken off really fast in a car, 0 to 60, not 0 to 109. If you take off really fast in the car, if you have a fast car, then it's going to throw you back in the seat, right? Your acceleration is steeper here, and then, like, whenever you're going faster, it's going to take it longer to get there. So, like, to go from 0 to 60, you know, this car can do it in 2.5 seconds, but it's going to take it a lot longer to go, you know, 120, right? It'll take it a lot longer to get to 120. That one, I'm sure, will go to 120. Most cars can't make it there, for a lot of them anyway. So we're supposed to estimate the car's speed after 2 seconds here. And I did this on purpose right here. I did not label the axes. But what is on our x-axis? What does it tell us here? Seconds. And what is on our y-axis? No. Kilometers per hour, because it tells us F of t is kilometers per hour. So that's what we're dealing with here. Okay? So, estimate this car's speed after 2 seconds. So, right here. It's what it's asking. Estimate the car's speed. What would you say? 91 kilometers per hour. Because we're looking at a different type of graph this time, right? It's not distance and speed. We don't have to figure it out if it asks us about speed. All right, so we're just reading the graph for this. This is definitely not, you know, calculus math at this point. At what time on the interval from 0 to 2.5 is the car traveling at the highest speed? Okay, Daniel's right. Why is it 2.5? So for this, it's at 2.5 seconds, right? Because at this point, your highest speed is right here, because this graph is giving us speed, right? So this is the highest point on the graph right here. So 2.5 seconds. We're at 97 kilometers, because it told us that over here. So these are just reading this straight off of the graph. But what about if we have to do this? Estimate the car's acceleration after 2 seconds.
We have to make that line that goes unset.
So acceleration is your change in your speed over time. So here, and acceleration in this particular case is going to be kilometers per hour per hour. All right. Okay, we're going to do some. We'll have to do some converting. All right. So. Oh wait.
Yeah, velocity squared equals delta t.
Delta.
Well, it's not like, I don't remember. I choose to forget it.
It's changing velocity over time is what it is. So delta v over t.
V squared equals John, it's little triangle t. That's change of time, right?
Yeah. I don't know about a v squared there. It'd be delta v over delta t. That's what we're looking at. Change in velocity over change in time is what we're looking at here. Pieces of it. Pieces. But not total. Okay, so change in velocity over change in time. So if we look at like a tangent line here that I've estimated, let's say that we're right here. I know this point right here is at 2.5, 97, right? And let's say about right here, that would be at 0.670. Right, if I made this tangent line, this of course is an estimate, so it's not going to be completely accurate. So we would be looking at the change in velocity. I'm sorry about that. To get the most. Change in velocity over change in time. So our change in velocity would be 97 minus 70, right? Over change in time, which would be 2.5 minus 0.6. And this is kilometers per hour. And this is seconds, which is going to cause us a problem here. Here we've got 27 kilometers per hour over 1.9 seconds. Probably the easiest way to do this here is let's just change seconds to hours here. So what should we do to change seconds to hours? Divide by 3,600. So we're going to have 27 kilometers per hour. You could use a chart here. I'm just going to do 1.9 divided by 3,600. It's 0.000528. So 27 divided by that number is, hold on. I'm doing something wrong here. What have I done? Okay, I take it back. We don't want kilometers per hour. Sorry, I should have said. I take it back. We want meters per second because that is for what our g-force is. So, alright. I do not have time to do all of this right here. We're not going to. I'm going to tell you that I'm going to convert it for you. 3.472. I should have just given you hours there so we can do this more easily. But meters per second. 9.81 is the acceleration due to gravity. So at this point, the car is not really, like, you don't have a lot of g-forces on you throwing you back into the seat, right? Because that's not the case. Over here, if we figured that out, it'd be much steeper. And so we want to know when the acceleration is the highest. What would you guys say for the acceleration being the highest? 0.1 would be a good right after takeoff here is when you're the steepest. And I'm not going to go through the estimating the acceleration just because we need to move on because we got another thing to do, which is quick. At this point, your acceleration due to gravity, or acceleration is going to be more like 5.6 or something. You'll feel a lot more force pulling it back here, I think. Oh, that looks like a messed up there. Actually, that might have been 11.1. That might have been more than 1G. So, like, if we wanted to know the number of G's that you're experiencing here, you just divide by 9.81, and I'll tell you the number of G's. Actually, I think I was looking in the wrong spot. I think this is that last one would be like 11.1. So if you divide it by 9, you're going to be a little over 1G pushing you back into the seat if you're driving this car. All right. Question is yeah, let's do this. There's only 2 questions. Okay. Ms. Hurl is trying to get all of the books returned to the library before summer begins. It is 10 days before the deadline. The number of books still missing is given below. Estimate the rate in which books are returned in books per day on day 1. So if we want to estimate the rate that books are being returned on day 1, we need the number of books per day. So we would use the closest points, right? So we would have, how many books were turned in here? 7 over 2 days, right? So 7 over 2 would give us 3.5 books per day. All right, so we could estimate that rate that books are being turned in. I mostly gave you this example. I know nobody's doing this with the books coming into the library, but I wanted to give you something that didn't have speed and acceleration so that you can see it can be done with different types of units as well. And so what about on day 7? What would we do for day 7? Same thing, but we'd use 8 and 9. So, no, 5 and 8. 5 and 8. Back up. So how many books were turned in? 22 over, what do we have here? 3 days. So that would give us 7.3 repeating books per day. So books are being turned in at a higher rate over that time period than they are at the beginning. There. So that sort of gives you an idea of looking at those things. So because we are getting close to the end of class, you want to go ahead and I've got a couple of things. Okay, this is going to be homework. It says classwork, but it's going to be homework because we're running out of time. And I'm also going to give you the notes that we're going to do things fairly quick. Yes.
Oh, that's what was on that thing on the candle.
Yes, it was going to be last night's homework, but I just need to change that plan because I don't know that I ever got through those things for today. I always talk about something else. Also, my change that Oh, did I give you this one? Oh. Okay. Yes. What? What did you say? Oh, you didn't. Which one did you not get? Notes? Neither one. everybody got one now?
All of this
Okay. Okay. This worksheet I want you to do for me for homework. And then you're going to have one other thing for homework. And that will be the college credit survey. So if you'll go to this website right here that's got a link to, you want to click AP Calculus AB. There's also BC. That gets you credit for Calc 1 and Calc 2. You're in AB. You only get credit for Calc 1. And you can look up whatever college you want to go to. And so I want you to look up, like, for example, I'm going to pick one that I know sometimes. North. There we go. North Carolina State University. So it will tell you AP Calculus. Oh, they have to change this. Well, no. Okay, so AP Calculus at State, it's a little bit confusing. So if State's one of yours, you can use this right now. You have to have a 4 for MA 141, which is, I believe, going to be your math and engineering calculus. They have two separate calculuses at State. If you get a 3, you can get credit for 121, which is like business calculus. So some majors may only require you to have that business calculus. So a 3 will get you credit for that, but if you're going into like a science or engineering or math, then I think you have to take that 141. I picked State specifically because I know that one is a little bit confusing. Most of them look different than that. Yes. Chapel Hill that one's also a little confusing because it's not really a 2. That one. Okay, so I think what happens at Chapel Hill, I wish they would tell you what these courses are. You could go look them up on Chapel Hill's website, but I'm pretty sure what it is that if you make a 2, they give you credit for pre-calculus. I think these courses are like a pre-calculus class. And if you make a 3, then you get this 231 right here, that's calculus. I believe is what they do at... So if you make a 1, they're probably going to make you take pre-calculus whenever you go to Chapel Hill. If you make a 2 and you go to Chapel Hill, you will place out of pre-calculus and you'll start in Calc 1. And if you make a 3 or better, then you get credit for Calc 1. So Chapel Hill takes a 3.
3 is like the GPA, or the score they get.
The AP score, yeah, 1 through 5.
3.5 would be a B.
Well, it does not transfer it just transfers as credit. It doesn't affect your GPA once you go there.
Yeah.
So it would just transfer as credit.
So the 4 and A, or what is
it? Won't be an A, B, C, or D. It's just credit or no credit.
Oh.
Yeah, so it won't affect your GPA whenever you go to college.
Yeah, I was just wondering about
But it'll give you credit for it, so you got those credits. So like if your degree requires you to have that, you've already got that credit checked off.
So much credit for how good you do in the class? Is that what it's saying?
If you make at least a 3, it doesn't matter. At Chapel Hill, if you make a 3, 4, or 5, you get credit for Calc 1.
Okay.
So,
That's in college, not
yeah. Now, if you made a 3, a lot of students who make 3s, usually if they have to have Calc 2, they'll decide to take out Calc 1 over again in college just to be sure they really got it. Now, if you don't have to have Calc 2 and 3, you take your credit for Calc 1, you say, thank you very much, I'm probably not going to take any more math classes, right? You don't really care about retaking it. But if you got to have 2 and 3, sometimes you might want to retake it. So anyway, you're going to do this. There is a little quiz here that you're just going to tell me, look this up, figure out. You may not have a specific career in mind. Just pick one you might be interested in, or you can tell me a couple if you would like. So you can do that for me. That's going to be your homework in that worksheet. We need to get these notes done though. Or we can do it. We can do it quickly. It's not that hard. Yes. Do like we were doing in class, like draw a line or use the chart. Yeah. So actually calculate, but know that your answer may be a little bit different from Addison's because you might estimate differently. Not just like that looks like 7. Okay, limit notation. These are the notes that you've got there. Okay. All right, limit notation. All right, so we did not do any limits in pre-calculus, and we should have, but we didn't do any limits in pre-calculus. We still did a whole lot more, apparently, than my pre-calc class did in Math 3, because there's some holes that I'm noticing are there today. So, got to catch them up. But we did not do any limits, so this is all brand new. So, this is what we call like the informal definition of a limit. I know that sounds crazy because it looks long and complicated. But given a function f, the limit of f of x as x approaches c is a real number r if f of x can be made arbitrarily close to r by taking x sufficiently close to c but not equal to c. If the limit exists and is a real number, then the common notation is limit as x approaches c of f of x equals r. Okay, alright, so let's draw a graph here. Arbitrary means like, yeah, it's sort of abstract, it's not exact. That's why this is the informal definition instead of the formal. The formal is way worse than this, so you don't want to learn. We're not required to do that. You might want to learn it. You can. Alright, so let's just say we've got a curve. Right, this is our f of x. Okay? Alright. So, we've got some point on this graph here. And we're going to call its x-coordinate c. Right here. And it tells us we have r is your f of x. So r is the y coordinate. Okay, so this is what this is saying. Okay? This is saying if I have a function f of x here, and I put a point somewhere, it could be, let's say, right here. As my x-coordinate gets closer and closer and closer and closer to c, my y-coordinate will get closer and closer and closer to r. So as this point moves here, as your x gets closer to this c value, as you get closer to here, then your y-coordinate will get closer to that r value. Okay? So we will look at this more in depth. Today I really am just focused on notation and what this means, not understanding what the picture means so much, but being able to translate from words to the notation. So let's look at what I want you to be able to do today. So all of these are going to start, this LIM, this is the limit. I know you don't understand what a limit is right now exactly. So the limit of this part right here is your function. So the limit of this function, and then you would say as x approaches.
Wait, is it like that little group thing that's unlimited rather than
The summation, like this one,
yeah.
it's a different thing, but it's,
Yeah, I know. But
yeah.
It's like more limited.
Yeah.
Okay. Oh, that's easy.
Alright, so like if I wanted to write this out in words, I would say the limit of x squared plus 7 as x approaches 5. Or you could say the limit as x approaches 5 of x squared plus 7. The order is not terribly important, which put that there. Yes. No, not really what it means. Just how to say it right now is all I really need out of you. Yeah. So now here is something important that we're going to see tomorrow what it means. But right now, notice how I've got a negative right here, but it's behind the A. So this right here is not negative A, because that negative is behind it, right? So this would be the limit of g of x. This part right here as x approaches A. This part right here, the negative behind, means from the left. When you think about your coordinate plane, your negatives are over here on the left, right? On the x-axis. This is x-axis, this is y-axis. You've got negative over here, positive here. So if you see that little negative behind this number right here, or letter, that means from the left. We will look at some of them. So if it doesn't have either one, if it's from 5, it's from both sides. You don't have to say from both sides because we assume it's from both sides. But we will also look at some that are from the left, and then we will also see some that are from the right. I'm going to skip that one. Oh, do I not have one that's... Let's change that to a plus just so we have one from the right. Okay. So, like for this one, we would have the limit of... all of this stuff right here. So the limit of this equation as x approaches 1, and then I changed it to a plus. It's a negative on your paper, but we're changing it to a plus from the right. Okay, I'm going to skip ahead. This one's the same, but it says x approaches infinity. Sometimes you see infinities there. That happens. All right, let's skip ahead to 5. All right, so this time we want to write the limit notation. So we've got a function f given to us. Find the limit of f of x as x approaches 3 from the right. So we would have limit LIM. Underneath it is where we put x approaches. What does x approach? 3. Do I need anything behind it? A plus sign behind it because it's from the right. And then over here we would put square root of x minus 3. So if we want to do 6, we've got the function as x approaches 9 from the left, so limit x approaches 9, so x arrow 9. What do I need to put behind it? A little negative there. And then you could put e to the 2x plus 3. Or you could put f of x because it's equal to that, so you could put f of x if you wanted. Alright, now let's look at this next one. It's wordier. Okay, so for a function f of x equals x plus 1 over x minus 3, f of x can be made arbitrarily close to 3 by taking x sufficiently close to 5 but not equal to 5. Alright, so arbitrarily close, sufficiently close, it should tell you you're doing a limit. So we're going to have limit. And then we've got our function over here, x plus 1 over x minus 3. Okay, what is x approaching? What is your x getting close to? 5. Okay. Now, in this case, it tells us what f of x is getting close to. It didn't do that on the other ones. So, f of x is what the answer is. So, this would equal 3. On the other ones, it was just the expression. It didn't tell us what the answer was. But this f of x getting close to 3 tells us the answer. There. So, you'd have it equals 3 there. And it's time to go. So that's good enough for today. So there's no homework to do with this. It's just sort of like an introduction that we'll need tomorrow when we're working on stuff. The homework is the 1.1 worksheet and the college credit survey. Okay? And I'll pass out white.
I wrote it down.
Oh, thank you.
Oh, I wrote that.
Anybody else have batteries? Your mom sent batteries.
I don't remember now. Well,
She had ordered some, I think. So, I mean, you can keep those.
okay.
Or if you don't need them, I'll take them.
Oh, there we go. We've got it.
What about this?
I don't know.